In our previous tutorial, we introduced you tree data structure. There we learned properties of trees, some terms that are related with trees, and also learned the application of trees. Now in this tutorial, I'm going to teach you a special kind of tree called binary tree. So what is a binary tree? A tree with at most 2 children is called binary tree. Here we draw a tree with 8 nodes. Node A, B and C each has 2 children. Node E has 1 child. And node D, F, G and H have 0 child. In this tree, no node has more than 2 children. So we can say it is a binary tree. A binary tree can have 0, 1 or 2 children. Based on the property, we can categorize a binary tree different types. A single node is a binary tree because it has 0 child. It is another type of binary tree. It has 1 child. And this is also a binary tree. It has 2 children. Now we learn different types of binary tree. A tree with 0 or 2 children is called strict binary tree or extended binary tree. See this picture and say, is it a strict binary tree? No, because node E has 1 child and it violates the condition of strict binary tree. I'm gonna delete this node H. Now it is a strict binary tree. All the nodes has either 0 or 2 children. In such a case, the node with 2 children are called internal nodes. For example, A, B and C. And the nodes with 0 child are called external node. For example, D, E, F and G. Next one is complete binary tree. A binary tree is said to be complete if all its levels except the last level have the maximum number of possible nodes, and all the nodes at the last level appear as far left as possible. See this picture and say, is it a complete binary tree? No, it is not a complete binary tree because in the last level nodes are not appear from left to right. I'm gonna save this 2 node to the left. Now it is a complete binary tree. If we know the level number, then we can find out the maximum number of nodes present to a level. Root node is assigned a level number 0 and every other node assign a level which is 1 more than to its parent. So B and C are at level 1, D, E, F and G are at level 2 and H and I are at level 3. So the maximum number of nodes to a level is equal to 2 to the power L, where L is the level number. Level 0 has 1 node because 2 to the power 0 equal to 1. Level 1 has 2 nodes. Level 2 has 4 nodes because 2 to the power 2 is 4. And level 3 can have maximum 8 nodes. Here we draw only 2 nodes, but it can have maximum 8 nodes, something like this. If all the levels of a binary tree is completely filled, then it is called perfect binary tree. So now we can say this is a perfect binary tree. The height of a binary tree is the longest path from root to the leaf node. For this tree, height is 3. If we know the height of a binary tree, then we can find out how many nodes are present to a perfect binary tree. Number of nodes of a perfect binary tree is equal to 2 to the power h plus 1 minus 1, where h is the height of the tree. For this example, h equal to 3, so we can write it as 2 to the power 3 plus 1 minus 1. 3 plus 1 is 4, so 2 to the power 4 is 16. 16 minus 1 is 15. So this tree has 15 nodes. Let's count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and 15. Well, conversely, if we know the number of nodes present to a binary tree, we can calculate the height also. If the tree has n nodes, then we can write n equal to 2 to the power h plus 1 minus 1. Now solve this equation. We can write it as n plus 1 equal to 2 to the power h plus 1. Then h plus 1 equal to log n plus 1 base 2. So h equal to log n plus 1 base 2 minus 1. For this tree, n equal to 15. If we put here 15, then we get log 15 plus 1, which is 16. Log 16 equal to 4. So 4 minus 1 is 3. So the height of this tree is 3. Height of a complete binary tree can be calculated as floor of log n base 2. Perfect binary tree is also a complete binary tree. So for perfect binary tree, we can also apply this logic. Here n equal to 15. So log 15 equal to 3.9068. Here we take only the integral part. So the height of this tree is 3. Next one is balanced tree. A binary tree is said to be balanced if the difference between height of left and right subtree for each node of a tree is at most 1. The difference between height of left and right subtree for every node may be 0 or 1, but not more than 1. Now, what is height of a tree? The height of a tree can be defined as longest path from root to leaf node. For this tree, height is 3. A tree with at most one node, height is 0. And an empty tree has height minus 1. Empty tree means there is no node in the tree. We can calculate the difference between height of left and right subtree as absolute value of height of left subtree minus height of right subtree. Here I am going to calculate the difference of height of left and right subtree of node C. This is the left subtree and this is the right subtree. Height of left subtree is 1 because there is one path from root to leaf node. Similarly, height of right subtree is also 1. So 1 minus 1 is equal to 0. So this is a balanced tree. Now consider the root node. This is the left subtree and this is the right subtree. Height of left subtree is 2. Height of right subtree is also 2. So we find the absolute value of 2 minus 2, which is equal to 0. For a perfect binary tree, the difference between height of left and right subtree for each node should be 0. Now I'm going to delete some nodes from this tree. Now calculate the difference for node C. It has no left subtree, so height is minus 1, and the height of right subtree is 1. So minus 1 minus 1 is minus 2. The absolute value is 2. Difference is more than 1, so it is not a balanced tree. Let's add here a node as left subtree. Now the height of left subtree is 0 and the height of right subtree is 1. So 0 minus 1 equal to minus 1, and we take here the absolute value, which is 1. So now it is a balanced tree. Next we learn how to store binary tree in memory. We can store binary tree in memory in two ways. One is linked list and another is array. The main requirement of any representation of tree is that one should have direct access to the root node, and for any given node, one should have direct access to the child of that node. This is the linked list representation of a tree. Each node contains 3 fields. Middle field contains data, Left field contains the link or address of the left child, and the right field contains the link or address of the right child. Since it is a binary tree, that's why it has at most 2 links. In C or C++, we can define a node as structure. We have 3 fields. One is data field, which is of type character. Here we declare the data field as character, but you can declare it as any type. Then we have 2 pointers to node, one to store the address of left child and another to store the address of right child. Linked list is the most common and easiest way to represent tree in memory. Next, we will learn how to store tree elements using array. Array is mainly used to store a complete binary tree. Here we draw a complete binary tree. Now we store the elements of the tree to an array. First, I'm gonna numbering the nodes. Root as 0, left child is 1, right child is 2. We're numbering the nodes from left to right, 3, 4, 5 and 6. These numbers represent the indices of array. Here I'm gonna draw an array of 7 elements. I'm gonna store A at index 0, B at index 1, C at index 2 and so on. Now the question is how we can identify the left child and right child of a node. For example, here I'm gonna choose a node arbitrarily. Let's say node C. Now, which one is the left child of node C? If we consider the root at ith position, the left child will be at index 2i plus 1 and the right child will be at index 2i plus 2. For this example, C at index 2, so left child will be 2 into 2 plus 1 is at index 5 and right child will be 2 into 2 plus 2 is at index 6. At index 5 we store F and at index 6 we store Z. So left child of C is F and right child of C is Z. This is it. Hope you understand. Please share it and click on the like button on YouTube. I'll be back with another tutorial. Till then, you take care.